So, friends, welcome to this lecture of geomorphology, and today we will continue with this fluvial geomorphology that we were talking in the last class. So, in the last class we have concluded that the Hottonian overland flow and this saturation overland flow, both they contribute this sediment as well as water to these stream systems. And today we will talk about this through flow system. This through flow, that means it is an interflow, it is otherwise called interflow. These are due to this cracks, this animal burrows, then decayed root canals like those. So, these are the free space. During running, this water moves through this free space quickly as compared to this other type of flows. So, this type of contribution or this type of quick movement of water through this open channels. So, they erode this material around them and finally, this contribute the sediments. So, this is one another type of flow as compared to this surfacial flow. These are the subsurface flow generally. So, these cracks and irrespective of this nature, either it is natural or there is artificial, the root canals, the animal burrows, they are a very good contributor for this sediment erosion and water flow from this river system. The principal difference between this Hottonian overland flow and the saturation overland flow is that saturation adds seepage pressure. So, the tendency for the loose particle to be moved downslope. Here if you see, if it is saturated, now see here this system is saturated. So, saturation it adds seepage pressure. So, seepage pressure, that means it is outward. So, that means it will lose the sediments, it will decrease the adhesive power of this grains, and once these sediments are loosed, that means it will be transported along with the water. So, sediment and water together they transport downstream. Thorough flow or interflow is what this water moves relatively rapidly through interconnected cracks, animals burrows, decayed root canals and other soil voids at shallow depths. Whether the deeper soil and the parent material are saturated or not, it is not necessarily, but here this is one another term, it is called thorough flow. Thorough flow means suppose we have cracks, we have burrows, animal burrows, we have root canals which is decomposed, that means there are free spaces available. So, during running some water they quickly flow through this type of cracks and this is called through flows or interflows. So, they also loosen the sediments from this inner part of the soil and or the subsurface soil, and this contributes sediment to this water. Through flow is within relatively large space in the soil or macropores and flows with turbulence that can erode and further enlarge the soil voids. Where this water moves downslope, but outward towards the soil surface, the seepage pressure reduces the effective particle weight and initiates sediment motion in a saturated surface. So, that means it is creating, it is increasing the sediment load or sediment contribution. The impact energy of raindrop easily disturbs and entrain the sand and small aggregates of sand, silt and clay, and if the ground is saturated, water and sediment begin to move downslope. When we are talking about a stream, that means we are taking a stream, water is flowing, along this water sediment is flowing. So, now we need water and sediments both to create a stream. So, in this way we are creating water, that means through rain water, through groundwater, and we are entering sediments particles, and due to saturation, we are losing the sediment particle, we are loosening the sediment particles and due to increase in the seepage pressure, and finally, we are contributing those sediments with the water. So, now we have water and sediments both are transporting, that means we are approaching to create a stream. In an experiment, a wire screen placed in few centimeters above the surface of this surface to break the raindrop impact without decreasing the precipitation intensity decrease the soil losses by 90% or more. So, that means if we are creating a shield somehow it is here it is a net. If you are placing a net on the soil surface and allowing this raindrop to interact with the soil, as compared to the barren land, this soil loss or this sediment particle to lose from the soil, the probability increases decreases 90%. So, that is why it can, if it is applied to this real world, this is like this vegetation cover, where this vegetation is covered, vegetation cover is there on the surface. So, that means here this sediment entrant or the sediment losing by raindrop, it decreases by 90%. That is why vegetated area they contribute less sediment as compared to barren land, and in vegetated area there will be more infiltration as compared to this other part. On bare gentle slopes, the scattering effect of impact surfaces channel formation and muddy water flow as a thin slow moving layer, that is called sheet flow. Here sheet flow, it is another type of flow, that means a thin film of water, it is flowing on the surface carrying the sediments, and very interestingly sometimes you can notice that the sediment is floating, the sand particle is floating on the surface due to surface tension. So, this is a sheet flow. So, it forms on the gentle surface and it is sediment laden water, it is flowing as a sheet of material. As slope increases, helical threads of secondary curve develops in this layer of water, which are capable of additional sediment scores. Now, you see it in initial stage a sheet flow was occurring. So, once we are increasing the slope, that means here you see this type of movement, that means here we are increasing slope, this type of helical movement, we are introducing the helical movement, and helical movement they are capable of eroding more sediments as compared to the sheet flow. So, that means by this way, by different type of movements, by different type of slopes, different type of landscapes, vegetation cover, without vegetation cover, we are approaching to create a stream with water, sufficient sediments within that. So, here first order streams or the rills they are developed. So, rills that means very narrow, very small, even if it is not mappable scale. Rills are not of mappable scale of 1:50,000 scale. So, here at some threshold of erosional and transportational energy that combines the factor of rainfall intensity, grain size, cohesion, infiltration capacity, slope and surface micro relief, the threads of higher velocity and more turbulent current erode small channels or rills. So, these are the characteristics features. So, all those characteristics you will find in the rills. So, if you see here, these are the rills, these are the rills. So, rills they grow on the sloping surfaces and finally, they grow headward and erode more regions. They expand this area of a river and they contribute sediments from these headlands and contribute to the downstream. So, they play major role in expanding a river systems. The headward propagation of rill is then limited only by the ability of conventional fluvial transport process to remove the material provided by these seepage pressures. So, that means if we are removing this material which was contributed by the rills, so that means we are allowing the rill to grow further. The process is called piping, is a common method of rill initiation. Piping, that means simple percolation. Now, if you see here, it was an experiment and here these are this, if you take this, it is a surface expression, but here if you zoom it, you will find this type of cavities, small cavities, that means it is going down, water is percolating down. So, this cavity, here this cavity, they will mix with their coalescence with time and finally forms a rill. So, in the surface the rills or the initial time, if you see these rills, they are simply their points through which the water is percolating downward, and with time these points they grow their size and their coalescence and forming a linear channel, that is called a rill. So, a rill, it collects surface runoff at its steep headward end and the resulting waterfall migrates upstream extending the reel into previously undissected uplands and capturing other reels. If you see here, suppose here if this is a reel which is growing and this way the reel this is growing, now two reels they are meeting here. Similarly, here this reel is growing and it is capturing here, this reel is growing and capturing here, this reel is going and capturing here. So, there are different reels they are joining together here. So, reel that collects surface runoff at its steep headward end and the resulting waterfall migrates upstream. Now, you see here once we are creating reels and in a sloping surface is there. So, the reel will migrate upstream. So, more and more upstream it migrates, more and more water it collects, more sediment it collects, and finally, it is expanding the river area, river basin area. So, basinal area increment these reels play major role. So, increase of this river basinal area. On barren slopes, reels can be observed growing headward at a rate of centimeters per minute or faster. So, it is very noticeable in the arid regions or this regions which is dry. Even if in front of you once there is if there is a rainy the heavy rain and if you notice it, you will see these reels can very fast they can migrate and more sediment can easily be eroded and it can further moved downward. So, they tend to be parallel with each other rather than from the dendritic network, because each is growing headward on the steepest local gradient. So, here these reels if you see they are mostly parallel to subparallel with each other. By the internecine of this surface few centimeters deeper than this adjacent interflow area, each reel side and head becomes a local discharge area for the shallow through flow. So, here through flows occurs and reels develops and further increase of reels, further aerial growth of these reels they collect more and more sediments and reel development becomes a dominant over creep surface. Creep surface you might be remembering when we were talking about this mass wasting process, and sheet flows on this convex hill slope a few hundreds meter down slope from this ridge crest and slope convexity begins. So, these are these areas they are the potential places where reels develop, and there is a particular type of erosion that is called sapping. Sapping that occurs where the land surface interacts the water table or groundwater table and spring emerges there. So, if you see here these are the loose sand and this is cross cutting, the groundwater table is cross cutting and the water is flowing downstream here. So, it is eroding this way and further this erosional process they will expand in this way, similarly it will expand in this way and finally, it is forming a surface where permanent water table will cut to the surface and there will be generation of streams, and this is the situation. So, there erosion by groundwater flow undermines the overlying sediment and rock and cuts a steep headed reel or channel that can expand headward and branch into drainage network even without overland flow. Sapping has been involved to explain drainage network on Mars as well as those on the earth. So, if you go to the mostly this sapping you will find in the coastal areas where this slope is very less and this groundwater table is very shallow. So, there at some places you will find this intersection of slope and the groundwater table and finally, this permanent stream or new stream that emerges out, that is called sapping. So, this has been interpreted this Mars surface that the sapping might have played major role in reshaping this Mars surface as evidence available this stream nature or this whatever these paleo channels they are available in this Mars surface, that can be interpreted to this presence of this due to this sapping process. So, these are some of these photographs from this Martian geomorphology and Martian surface. You see these are these channels and these are the channels. So, here probably this the interaction of this intersection of this groundwater table as well as the surface. So, this is called sapping. So, once reels they join together and the width increases, they form gullies. So, gullies is a stream channel with discrete cut banks and often with a steep head that distinguishes it from reels. So, these are the characteristics, that means it has discrete cut banks and often with steep head that distinguishes it from the reels. So, reels with further growth they convert to gullies. Gullies grow headward rapidly enough to capture adjacent reels and commonly develop a branching network of tributary channels with dimensions scaled to their drainage area. They are the first step in the fluvial dissection of landscapes. So, this is very important to say. So, gullies they are the first step for fluvial dissections. So, whenever we go for mapping, reels we cannot map, but gullies can be mapped. So, that is why gullies that present they are the first step for the fluvial dissection of an area. So, here if we are increasing our scale mappable and it is not mappable, but this is mappable and this is mappable. So, that means reels further growth it is gullies, further growth it is valleys. So, these are these first order streams, as though actually these are the first order streams, but we cannot map it in our mappable scale. The scale we generally used in mapping 1:50,000 scale, we cannot map it, that is why we ignore it. And if we map it, this map will be very clumsy, thousands of lakhs of reels will be there. So, that is why we ignore it and we consider this is they are the first order streams. So, there are steep usually bare banks are unstable, scarred by slumps and soil tuffles. Gullies in arid and semi-arid regions are likely to be flat floored, wide and steep walled because of these strong vertical and columnar joints, typically dry soils. So, when dry, which is the most of this time, they are floored with coarse alluvium. So, these gullies they have the transportation capacity more transportation capacity than the reels, because this width is more, water capability is more, sediment is more, that is why they can transport more sediments. Some channels they are occupied by permanent streams that flow throughout the year, other have intermittent streams, and still others are used only briefly during immediately after precipitation, that is called ephemeral streams. So, intermittent streams, permanent streams and ephemeral streams, and few minutes back we are talking something about influent effluent river systems. So, now here it is mentioned rivers in humid regions are called effluent because they receive contribution from groundwater. So, once we are receiving from groundwater, they are called effluent river. Here their groundwater is there and it is contributing from there. So, this is called effluent streams. River is in arid regions generally lose water to this ground in addition to losing it by evaporation, and many of these dry up entirely without reaching this sea. They are called influent stream. So, influent means river is going down, influent. Effluent river is when water is coming up. So, if it a groundwater table it is receiving water from this river or from the channel, that is called influent, and water or the stream which is receiving water from this groundwater, that is called effluent. So, mostly the arid region rivers which is groundwater is much below the surface, during rainy season whatever these ephemeral streams are there, this water percolates down and they are called influent streams. And in the humid regions where what groundwater table is very close to the surface and somewhere this groundwater is contributing to this river system, and that is called effluent streams. So, now we will talk about some of these practical aspects of this river system or channel system. that is gauging station, rating curves and hydrographs. What are those things and what is its utility in fluvial geomorphology? Gauging station, that means measuring stations. We measure, what we measure? Discharge, water discharge, sediment discharge, water fluctuation, time with time and space, because in a river in the entire length we have number of gauging stations. For example, if you see here, these are the position of the gauging stations in the Ganga plain rivers, these points. So, that means one point to another point we gauge, we measure how much water is discharged. For example, water is discharging, this much amount of water is discharging here, and at the downstream the water is increasing or water is decreasing. So, that means we can say how much water is being contributed there or how much water is lodging in between. So, how much sediment is transporting here, how much sediment is reaching that level and how much within the floodplain, within that river bed, how much sediment is depositing. So, that means these are useful for planning purpose, for applied aspect. And rating curves and hydrographs. Rating curves, that means this water fluctuation graphs. So, at the annual water fluctuation graphs, from that we can say where there were floodings, from the rating curve we can say where there is flooding and what is the time taken for the flood water to reach from this station to that station. And for this prediction purpose, for this alarm purpose, for this management purpose, we need this type of measurements. And at these stations or these gauging stations, usually the segments or reaches that are straight. Now, it is some requirement are there, prerequisites are there, where we will place these gauging stations. We cannot space it everywhere throughout this river length. So, we choose those spaces where the river reaches or segments they are straight and have carefully measured and relatively stable cross sections, where suppose there is a river cross section, there is changing with time. So, that means river is getting wider and wider and very frequently river width changes. Those are not the suitable places for gauging station establishment. So, that means we have to choose those places, either it should be a straight segment and this cross section area should be relatively stable. The discharge, the water surface level, the channel shape, stream velocity, amount of dissolved and suspended minerals of the sediment and other variables are periodically and continuously recorded. So, these are the works of these gauging stations. These are this material or these are these parameters that we measure at these gauging stations at different places along this river basin or the river discharge. So, here discharge Q is the amount of water passing through a channel cross section per unit time. It is defined as Q equal to V into A, where V is the average flow velocity, because average flow velocity means velocity at different levels. If we average it out, similarly velocity at different lateral level and vertical level, we average out at a particular cross section and we assign this velocity. Because if you see here, the velocity contours here in a river cross section 1.3, 1.5, 7, 1.9 like this. So, that means the velocity is more at this middle part. Similarly, you are going towards the bank from this middle, going towards the bank from the middle, the velocity is decreasing. Similarly, going towards depth, the velocity is decreasing. So, that means we average out and assign either the vertical velocity as well as the lateral velocity, we average it out and assign a number here. So, this is called average velocity. How it is measured? Here we segment into different columns and for each column from top to bottom we measure this velocity and assign a number, and finally, we average out for each columns and give this velocity for a particular cross section So, that means here V is the average flow velocity through a cross section of area A. This is area and this Q will be the discharge. In channel flow, area is the product of channel width and average depth D, and the definition of a discharge is commonly Q equal to W d V. So, this is the discharge of a river. Q is expressed in unit of volume per unit time typically meter cube per second or feet cube per second. To determine Q with necessary precision, depth is measured at close intervals across a channel and the velocity at several depth is measured at each interval, then W, D and V calculated for the particular cross sections. So, after measuring these cross sections, we measure how much water is flowing per unit minute or per unit second in that particular area. So, this is the discharge. Having determined Q for a variety of conditions, a rating curve or a rating table for this station is established. A variety of conditions, that means in a dry season, pre-monsoon, during monsoon, post-monsoon, flood situations. So, all these times, all these different situations, this Q or discharge is measured and it is plotted with time. So, with plotting, that means we are getting a rating curve or rating tables for a particular station, that is valid for a particular station. Similarly, for other station we measure and different rating curves we measure, we compare whether this, but not necessarily this rating curves will be matched together. For one station is independent to another station, because the discharge is different, the sediment is different, the width is different, the height is different. So, from which Q can be directly determined from this rating curve, from the water surface height alone, which is read from a calibrated vertical staff and a float operated water level recorded and installed in the station. Nowadays, we have sensors, digital sensors we are using at the bridge side, and here these are the rating curves, or these are these measuring stations where measurement is done, and nowadays through the sensors also we are measuring. So, the rating curves are prepared. A graph of discharge plotted against time at a gauging station is called hydrograph. So, with time, if you see here, with time and discharge. So, in this Ganga plain rivers, the discharge, because they are from glacier fed. So, during glacier melt and during daytime we will find more discharge, but that water which reaches at this gauging station, that may be in the evening. So, in the evening time we will get more discharge, because the water, this glacier melting in the daytime, this water percolate, the water at time needs to water to come to this gauging station from the morning to evening or from daytime to evening. So, that is why this hydrograph is a graph of discharge plotted against the time at the gauging station, it is called hydrograph. Depending upon vegetation, soil type, infiltration rate and host of other factors, the hydrograph reflects the precipitation in the watershed above the stations. So, whatever the information we receive from a gauging station from this hydrograph, it is valid for the upstream, not for the downstream. So, that means we can predict about this upstream situation, what are the soil type is there, what are the vegetation is there, what are the infiltration rate is there, and what are other factors are there, that all that can be told about this upstream from these measuring stations. Stations progressively downstream have broader hydrographs. So, that means if you see here in this figure, this is upstream and this is downstream, and further once we are moving up, it is station 108, station 302. So, that means we are further moving downward. So, this shape of this hydrograph you see, it is getting broader and broader. So, these stations progressively downstreams have broader hydrographs with flatter crest at progressively later times, depending upon the time required for the storm water to reach the station at various temporary storage within these basins. So, that means once we are moving downstream, the shape of this hydrograph is changing. A line connecting two low points of a hydrograph separates the base flow fed primarily by groundwater from the storm runoff. The stream responds to a particular precipitation event. So, here this is called base flow, that means this is the permanent water, it remains there, this is fed by this groundwater, and this is the storm water or the event water, which is either due to melting or something else, or storm or discharge or the rainwater, heavy rain or whatever may be. So, this rating curve, from the rating curve, if our hydrograph this part, it is called permanent flow or it is called base flow. The records of stream gauging stations are essential for the prediction of potential flood damage, stream pollution, other, other disasters, construction of a dam, bridge and flood construction, flood control structures. These records are provide a voluminous history of the stream flow. So, that means this measurement is important for this purpose, for the planning purpose, for the stream pollution measurement purpose, for dam establishment purpose, okay. So, bridge construction purpose. So, all this developmental purpose we are measuring this and we are creating these hydrographs. So, why we need this hydrograph and why we need a measuring stations? Because whatever the data we generate from this hydrograph or measuring station, we require for this purpose. For example, suppose we are going for potential flood damage, we want to predict it where this, when, what time this flood water will reach at which segment of this river basins. Similarly, in stream pollution, which part of the stream is getting polluted water and which part of the stream is more polluted. Similarly, other disasters like flood situations and suppose for example, we are going to construct a dam, which part is more discharging, which part of this river is contributing more discharge, and suppose we are establish a bridge or construct a bridge, whether the sediment characteristics, the sediment what type of sediment is passing through the saltation, suspension and traction, and it will damage this river the bridge pillar like that. Similarly, flood control structures we are going to establish. So, all those factors, all those purpose, we need this river data, we need the hydrograph data, we need the discharge data, the amount of sediment is discharged, amount of water is discharged, is not it. So, that means hydrograph plays a major role in planning purpose. So, I think we should stop it here and we will meet in the next class. Thank you.